Alright, let's take a look. Today we want to cover ions. We're kind of sneaking this one in because it deals with resonance as well. And then isomers. Wow, we're kind of finishing up quite quickly here. Alright, cool. So ions, we know that ions have either lost or gained electrons. So that means that whenever we find our total number of valence electrons, we either need to add or subtract electrons depending on the charge. The other thing it means is that we need to put brackets around our Lewis structure to indicate to somebody that, hey, there's an extra electron there because of this charge. This is something that I forget to do, so I have to remind myself constantly because I'm sitting there like, oh, I just done a bunch of stuff. Yay, I'm done, but I'm not. I need to make sure I put that on there. So if we take a look in H4+, this plus means that we've lost an electron. That means that this compound has a positive charge because it has more protons than it does electrons. So if we take a look, nitrogen gives 5 plus each hydrogen gives 4. That's a total of 9, but we need to minus the 1, so that equals 8. So let's try to draw this guy. Who's going in the center? Well, we have the unique rule. Nitrogen goes in the center here. Nitrogen, hydrogen, 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 hydrogen. 2, 4, 6, 8. Octet is fulfilled. If I were to move on here, somebody would say, wait a second, you have this drawn and you're only showing 8 electrons, but 5 plus 1 plus 1 plus 1 plus 1 is 9. So there's something wrong here. You're showing a structure that is not correct until you put the brackets around and then say, hey, oh yeah, but wait, it lost 1 electron. So that's that. That's pretty simple. Not much added here. Let's take a look at a number of valence electrons in carbonate. CO3 2 minus. Well, carbonate carbon brings 4. Each oxygen brings 6 for a total of 22. The negative 2 tells us that we're adding 2, so that's 24. I'm going to drop down here and put a carbon in the center. I'm just going to use that to do symmetry. It's a little bit nicer. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Well, we said we had 24 available, but I'm showing 26. Somebody might say, well, you're actually not even correct in this. Hold on one second. I know that there's something wrong with this because I have 2 extra electrons in my structure. So that means I'm going to need a double bond. Now this brings us into resonance because I could choose this one to put the double bond with, or I could choose this one, or I could choose this one. The problem here is that you've got to show all of them. So this shows resonance. I believe that's how you spell it. Resonance is how you pronounce it. So we're going to put the C in the middle, and I'm going to just start off by putting it with the top one. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Again, somebody's going to say, well, actually, we need to show that extra 2 negative. You can put 2 negative or negative 2. It doesn't matter. It's just like saying 2 minuses or minus 2 for the charge. So both ways are acceptable. That's one resonance structure. We then would show a double-sided arrow showing or. Could be like this. And then you're saying, seriously? Yeah. You won't have to do many of these. It's not a big deal. Since we have 3 oxygens bonded to the carbon here, though, we do need 3 of them. And here's the silly thing. Basically, scientists don't believe that any of these structures exist separately, but they all 3 exist at the same time. And this double bond we're going to call this electron delocalization, which means that, yeah, we know these electrons are probably in there, but these electrons here, they're basically being spread around, and that's that resonance thing. It's like basically it's almost like if we took this picture and merged all 3 of these, and basically gave like this area right here a little bit of extra electrons that could be passed around like hot potatoes. And basically what you would see is, okay, this is going to here, this is jumping down here, you know, it just keeps bouncing around, and that's like the resonating. But that's resonance. Notice again, each of these has a 2 added on because it's 2 negative. So here we have SO4. So pause this and try this on your own. 3, 2, 1. If you're not paused, then what else, right? So there is our skeleton structure. We have 6 plus 4 times 6 is 24, plus 2 because it's negative 2. So that gives us 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Don't forget, we would need to put that negative 2 there. Now you're saying, well, what about all the other structures? Well, we had the exact amount, so there's no double bond. You cannot show resonance unless you have a double bond that could be between 2 different things. So since we had enough electrons, we're good. If we only had 30 electrons, then sure, we would have to do a double bond around that. And then you would say, oh, well, what about sulfur, though? It would have more than an octet. Well, sulfur's down here. It's in the 3rd period. So remember that the 3rd period also has the D sublevel, 3D. Well, not maybe getting ahead of ourselves a little bit, but sulfur could actually take another set of electrons with no problem. But that's for a different day. So let's draw the structure of H3O. Well, again, uniqueness, who's in the center? H, H, H. 3 plus 6 is 9, but we have a plus, so that's minus 1, so that's 8. 2, 4, 6. These guys aren't getting any more because hydrogen only needs 2. 8. Big forget here, don't forget to do that. Cool, cool. Then it gets into the resonance. Because it's a shifty bond, so if you take a look with SO2, you end up with this, but you have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 is 2 more than 18. So that means that we could choose to put the double bond here or the double bond here. Well, that's not really a choice for us. We actually have to show both. So we show the double bond on the right side oxygen and then on the left side oxygen. That's resonance. It looks as if the bond can move back and forth. Actually, several electron pairs simultaneously move to create this effect. The actual structure is a hybrid of these two. As we said, we have that electron delocalization occurring here, but this is how we draw it in a structure form. Last topic today, isomers. Basically, isomers have the same chemical formula, but they have different structures. So if you have C2H6O, well, you might start with the C2s in the middle, and then the 6 H's, and then the O on one side. Well, that's not very symmetrical, but that is a compound. That is known as ethanol. Ethanol, and it works. I'm going to go ahead and, oh, they already put them down here, but I'm going to put them there too. And this is ether. Now, this looks symmetrical. Neither one of these is more right than the other. They're just two chemicals with the same formula. Ethanol is the alcohol that your body can break down. So this is what's found in the drinking liquors and stuff like that, or even in beer or wine. That is ethanol. This makes your body kind of have a lack of oxygen getting to the brain. It slows the functions down, and it gets you intoxicated. Ether has the same chemical formula, but it acts a little bit differently. Ether is an anesthesia, which can put you into kind of a different stasis. This is the drug that they use to kind of put you to sleep back in the day when they had first found ether. They found that if they could get you drunk and saw off your arm, you may go into shock still. But by using ether and putting you into a sleep and sawing off your arm, they could usually repair it and stabilize you before you woke up. So definitely two compounds that have different properties, even though they have the same formula. That is called an isomer. Isomerism is quite common in what we call organic chemistry, which is something we'll go into after this. Organic chemicals are basically the chemicals you study with the element carbon in them. That's the building block of life. Here it says that this can also be called ethanol or ethyl alcohol, and this can be called methyl ether or just ether. The methyl refers to one carbon on each side. With that, you should be able to do problem 3. You're to write 2 isomers of C4H10, so make sure you save space there. And then you should be able to do 5 and include the resonance structures for NO3. You also should be able to do page 17. Just draw the structures. Man, that's a crazy looking R. Just draw the structures. All you've got to do is draw them. If they show resonance, please indicate so. Other than that, page 17 is where you stop. The reason why we're not doing page 15 yet is because we have not done geometry yet, which we will use page 15 and 17 and the other pages to basically talk about geometry. That will get us in there. Excellent.